Alright, the first part of this video is just going to go over the two questions that you were to answer before watching this, just to make sure we're on the same page. Okay, so the scenario is we're looking at a biology class where historically the distribution of grades was like this, and we have data on a new section of the class, and we want to see if this data fits this distribution, or is it drastically different. So one way to do this would be to just take each individual letter grade and run a 1 proportion z-test on that. So P sub A is the true proportion of people who get A's, and for the first test we could just run it for the A's, a two-sided test to see if it's 0.15 or if there's significant evidence against that. We could do it for each individual letter grade. So we could write 5 1 proportion, or we could do 5 1 proportion z-tests to answer this question. That's a little bit cumbersome. So it would be nice if we could run one test which does this all at the same time. And this would be our null and alternative hypothesis for that test. So we've got each individual grade distribution proportions are what they were before, and the alternative would be that at least one of these is not what they were before. Okay, which means basically at least 2. Maybe the same proportion of people got A's, but the B's and C's were all messed up or different. Okay, so we have 325 students in a most reading class. Fill out the missing line in this table. So I expect 15% of students to get A's. So if I want to figure out what goes right here, it's 0.15 times 325. If I want to figure out what goes right here, it's 0.3 times 325, and so forth. So I've sort of done all this in the calculator, or will. And so here's what I've got in lists. I've got the actual number of people, and then I've got the expected proportion. So in list 3, I'm going to do 325 times list 2, and that's going to give me the expected amount in each cell. So it's 48.75. Let's see if we can rearrange this a little bit. So this would be right here, 48.75. This is 97.5. This is 130, 32.5, and 16.25. Okay, so these are the expected amounts. All right, so that was what you had to do on your own, and now let's kind of go through the other side together to see if we can figure out how to run this test, which is called a chi-squared goodness of fit test. So now I'm moving on to the back of the sheet. I filled in the second line of this table. That just comes from what we had above. So obviously, if we want to figure out sort of what is different than expected, we could simply take the observed amounts right here and subtract the expected amounts. Okay, a real simple way of comparing to see how far off we are from what we expect. So let's just kind of simplify that process in the calculator. So you can see that in L1 I have the observed counts, and in L3 I have the expected counts. So let's put in L4 the observed minus the expected. Okay, so this just happens to be where I have these. Doesn't really matter. Okay, and so these are the differences. So 40.25, 23.5, and so forth. So I'm going to go ahead and fill those in. Now, as you can see, some of these differences are positive and some are negative. The positive differences would indicate that the observed amount is more than expected, and negative would indicate that the expected is more than the observed amount. Okay? So we know in statistics when we have these positives and negatives and we want to make them all positive, what we typically have done is we have squared the quantity. So we're going to take the observed minus expected squared, but then we're going to divide by the expected. So this sort of scales it by the expected. And so if you look at the units of this, the observed minus the expected squared are in number of people in here squared. We've divided by the expected. then it's in terms of number of people. Okay, so let's go ahead and compute this, these quantities. And we'll do that in the calculator again. So you should be doing this with me and pausing the video. Okay, so we have the observed, which is in L1, minus the expected, which is in L3, okay, squared, all over the expected. Okay, these values right here are called the components of the chi-squared test statistic. And the bigger the value is, the more off that we are in this situation. So I'm going to go ahead and fill these in to this line of the table, and you can pause it and do the same thing. Okay, so if you think about we're running a significance test. Here is our hypotheses. We can define these parameters. So this is P, H, A. Okay, we'll talk about assumptions later. But then as far as the name of the test, to do this all at once, it's called the chi-squared goodness of fit test. And the test statistic is not Z, it's not T, it's actually called the chi-squared test statistic. And here is the symbol for, that's a chi-squared. And the chi-squared test statistic is simply the sum of the observed minus the expected squared over the expected. Okay, so that's taking these values right here and adding them up. That's the chi-squared test statistic, okay, for the chi-squared goodness of fit test. So let's go ahead and try to do that. Basically, I have these values in list 5, so I want to sum up list 5. Here we go. Uh-oh. Okay, so we had some technical difficulties. I'm back now. I'm going to sum up these values right here. Okay, that's are in list 5 for me. I'm going to go to math. Where the heck do I do this? Actually, I'm going to go to list second stat. I'm going to do math on the list. I'm going to sum L5. Okay, 62.53 is the value of my test statistic. Okay, so now, just like for a z-test or a t-test, there's a distribution. There's a normal distribution. There's a t-distribution. There's something called a chi-square distribution, which looks, first of all, chi-square distribution is always positive. And if you think about why that makes sense, you know, we're taking the observed minus the expected squared. That's always going to be greater than or equal to 0. So if we add up a bunch of numbers that are greater than or equal to 0, there it's always going to be greater or equal to 0. So this usually or always looks skewed right like this. And the chi-squared test statistic simply says how many standard deviations away are we from 0. Okay? So this is where we are, 62.53. And if I want to find the p-value, I just have to find the area under this curve. Okay? So we'll talk more about this in class, but each chi-square distribution, like a t-distribution, has a different degrees of freedom. And the degrees of freedom in this case is the number of categories minus 1. Notice it's the number of categories. It's not the sample size minus 1. The sample size is 325 here. It's the number of categories minus 1. So we've got 1, 2, 3, 4, 5 categories minus 1. So the degrees of freedom for this is 4. All right, so let's try to find the p-value. Let's just do this by exploring the calculator. When we found areas under distributions, before we used like CDF. Let's see if we have something in here. I'm going to go under distribution. Oh, there's something called the chi-squared CDF. All right, so I'm going to do 62.54 in this case, comma, hella big number, comma, degrees of freedom, which is 4. This is our p-value. And what we can see is that our p-value is extremely small. 8.48 times 10 to the 13th. 10 to the negative 13th. So that's like 0.000000000. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 848. Okay, that's the p-value. Clearly really small. And so we're going to reject that because the p-value is less than, any significance level that we take. And so if I look at the original null hypothesis, the null hypothesis said that the distribution of grades is the same as it was before. We're rejecting that. It's clearly different. All right, so the conclusion is there is significant evidence that the grade distribution in this new section is different than before. Now, what that means is, I don't know, different students, different grading, I don't know. But this is what our test shows. Now, as far as which grade impacted the decision the most, explain what it means in the context of the problem. Well, what we need to do to figure that out is look at this, the components of the chi-squared. Which of these contributed most to this high chi-squared test statistic value? Clearly the A's. There are clearly many more students who got A's than we expected, okay, for some reason or another. So the A's are the ones, and what does this mean? In this class, many more students got A's than expected. Okay, that's what that means. And we typically, when we do a chi-squared test, we drill down into the data to see which grades impacted things the most. Okay? All right, so you're going to now try a problem on your own. And this one deals with Skittles. The Skittles website claims that the flavors are distributed evenly or uniformly in each bag. So there's 5 flavors. I'd expect 20% to be grape, 20% to be lemon, 20% to be lime, 20% to be orange, and 20% to be strawberry, wherever the heck that color is, red. So we get a huge bag with a lot of Skittles, and we want to know, does this bag provide evidence against the claim here? Okay, it seems like I got a lot more orange than any other color, particularly more orange than lime. Is this enough evidence to say that we don't think Skittles is right? And so you're going to do that by doing a chi-squared goodness of fit test. So go through a similar exercise of what we did. Now, the one thing we neglected, and we'll talk about them in class, are the assumptions for this test. Okay, we're going to talk about that in class. But if you look at what we're doing, it's still phantoms. Okay, we can define our parameters, PA, so forth. We can do our null and alternative hypothesis. That actually would be right here. Okay, we have assumptions. We have the name of the test right here. We have the test statistic right here. We're obtaining the p-value here. We're making a decision here, and we're stating our conclusion there. So it's still phantoms. It's just a different test. Okay, and what we're really doing is testing many one proportions at the same time. It's called a chi-squared goodness of fit test. Okay, so you're expected to have watched this video, to have tried your best on this problem. You're going to turn this in, and tomorrow in class, this will speed up our discussion, allow us to move, to go deeper, and to move a little bit more quickly.